Good day. The topic is about lateral earth pressure for partially submerged soil and with surcharge load. Okay, so first, for lateral earth pressure for partially submerged soil, so with shallow groundwater table or saturated soil, so for the analysis, instead of the effective lateral earth pressure, we will therefore consider the total lateral earth pressure, the sigma H. So for our total, the sigma H, it is now equal to the effective, the sigma H prime, plus U, which is the pore water pressure. So for our sigma H prime, again, from our previous discussion, sigma H prime is equal to KO times sigma O prime. And for our U, that is the pore water pressure or the hydrostatic pressure, it is equal to gamma of water times the height. On the other hand, for the lateral earth pressure with surcharge load Q, so for uniformly distributed load on top of the upper ground surface, so what will now the modification? So for earth overburden, for the effective overburden pressure, so that is the sigma O prime. So sigma O prime, which is the total weight on top of the specific point. So sigma O prime is equal to Q, our uniformly distributed load, plus the summation of gamma prime times Z. Okay, so again, Q is the surcharge load, and our summation of gamma prime times Z is the vertical effective stress or the weight of the soil being considered. So for our sample problem, so figure 1.20 shows a retaining wall that is restrained from yielding. So the uniformly distributed load above the slope is 300 pounds per square foot. So determine the value of the lateral earth force per unit length of the wall. Also, find the location of the resultant measured from the bottom of the wall. Okay, so for this problem, so we need to determine the different values of KO, again due to the different values of our phi prime. Because for our first layer, phi prime is 34, while the second layer, phi prime is 30 degrees. Okay, so for our requirement, the requirements are PO, again, our resultant force, and Z bar, the location. So for our solution, again, by inspection, the direct formula or the equations are not applicable for this problem. Why? Because the first criterion as well as the second and the last are not satisfied. So for the first, our one homogeneous soil not satisfied. The second, no additional loading. So we have already Q. And the last, the soil is not saturated. We have already our shallow groundwater table. Okay, so using now the pressure diagram, so assigning now the different points starting at the very top of the slope. So that will be our point A. So at the interface of our two different layers, our point B, and at the base, that is point C. Okay, so for our earth pressure, the sigma H or the total is equal to the effective, the sigma H prime, and our pore water pressure U. So again, for our sigma H prime, that is KO times sigma O prime, while our U is gamma water times the height. And our sigma O prime is, since we have already our additional load, that is modified as Q plus summation of gamma prime times Z. So let us now compute these varying values of KO, which is 1 minus sine of phi prime, because again, the problem didn't or did not identified the condition of the soil, so the default is normally consolidated. So KO is equal to 1 minus sine of phi prime. Okay, so the KO now for the first layer, that is from points A to B, that is 1 minus sine of 34 degrees is 0.441. While KO from B to C, that is 1 minus sine of 30 degrees, which is equal to 0.5. Okay, so again, the flow of solution is from the sigma O prime towards now the sigma H prime, and plus U And finally, our sigma H, the total. So for our solution as well, since B is exposed to two different layers, two different phi primes, then therefore our sigma O prime later on be multiplied with two different values of KOs. So presented in table form, we have the points sigma O prime. Next is KO. So we need to add KO because again the different values of KOs for specific points. Okay, so sigma H prime. And we will now consider the addition of the pore water pressure or the neutral stress or the hydrostatic pressure and the total lateral earth pressure. So for our points now, we have points A, B, and C. Starting with our vertical effective stress, the sigma O prime. So sigma O prime is equal to, we have now at point A, Q, which is 300 psf, plus the weight on top of the soil, which is 0. So it is now equal to 300 psf. So carry over now the initial weight, that is 300 psf for point B. So that is now plus the weight of the soil on top of B, that is 110 PCF or pounds per cubic foot. Multiply that with the thickness of that layer, that is 6 feet. So the answer now is 960 PSF, the total weight at point B. And carry over the total weight at point B and adding the weight from B to C, we have now our effective for C, that is plus, again, we need to consider gamma prime. So gamma prime, since we are provided with saturated unit weight due to the presence of the shallow groundwater table, we need to deduct or subtract the value of the gamma of water. So for metric, that is 9.81, but for English, that is 62.4 pounds per cubic foot. For this problem, we have now 126 minus 62.4. So that is our effective or submerged unit weight. Multiply that with the remaining thickness of that layer, which is 14 feet. Our sigma O prime, therefore, at point C is 1,850.4 PSF. So assigning now next the values of our KO. So for KO, starting with KO from A to B, so exposing for A and B, 0.441. On the other hand, for the second, exposed to B and C, that is 0.5. Multiplying now our two values, the sigma O prime and KO, the sigma H prime is equal to 132.242 PSF for A, 423.175 PSF for B at the immediate top, and 480 PSF at the immediate base. While for C, that is 925.2 PSF. And in addition, we are done now for sigma H prime. Let us proceed to U, the pore water pressure. So for U now, so identifying now the location of our shallow groundwater table, at point A, there is no presence of hydrostatic force, therefore the value is 0. While at point B, since that is the starting point of the pressure, even though that is at the surface of groundwater table, the height of that water is still be equal to 0. Therefore, gamma of water times the height, that is 0, it is equal to a pore water pressure, which is 0. So from that point B, the surface of water, it will definitely increase uniformly up to point C with the value that is 873.6 PSF. And finally, since we have already the components, we can already determine our total. So for the total, that is the sum of our two columns, the sigma H prime and U. So at point A, that is 132.242 PSF. At point B, 423.175 PSF. At C, 480 PSF. And at B rather, base. And at C, that is 1,798.8 PSF. Okay, so let us now consider our different magnitudes. So presenting now the component pressure diagrams. First, our sigma h prime, followed with U, and finally our sigma h, the total. So for the sigma h prime, the magnitude at the top is 132.242 psf, while at B we have at the immediate top 423.175, and the base of B 480 psf, while the maximum at C is 925.2 psf. Connecting the different magnitudes, so this is already our first component. Next, for our pore water pressure, so at A 0, still at B 0, but starting from B, the surface of the groundwater table, it is uniformly increasing towards a value of 873.6 psf at point C. And summing now the two components, it is now equal to the total. First component is 132.242 psf. At B, we have at the top 423.175, and at the bottom 480 psf. While the total at C is now at the full magnitude of 1,798.8 psf. Connecting now the points, so we can already complete our pressure diagram. Okay, so we will now take the last. So for force, PO, and location, Z bar, so we will consider only the total lateral earth pressure diagram. So our PO and our location, Z bar. Okay, so using now our total lateral earth pressure diagram for our PO. So PO is equal to the volume of the pressure diagram, which is equal to the area of the pressure diagram times the length considered. So sample length for our example. But before we take now our 80 times L, since our diagram is composed of two different trapezoids, so we need to divide this into simpler shapes composed of two triangles. So therefore, we have already 4. So for our PO, it is now equal to, for the first, we have the green triangle, that is 1/2 times the base, 132.242 psf, times the height of this component triangle, 6 feet, plus the next, the orange triangle, which is 1/2 times the base, 423.175 psf, times the height, 6 feet, plus the purple triangle, which is 480 psf, times the height, 14 feet, plus the last, which is the red, 1/2 times 1798.8 psf, the base, times the height, 14 feet. Again, we need to compute individually the area which is needed for our location later on. So for our PO, it is equal to the quantity. The first area is 396.726 pounds per foot, plus the second is 1,269.524 pounds per foot. The third is 3,360 pounds per foot, and the last is 12,591.6 pounds per foot. And multiply this to our sample length, 1 foot. And for our PO, the total area now is equal to 17,617.851 pounds per foot. Multiply that with our sample length, which will yield now with the value of PO, that is 17,617.851 pounds, and with this orientation of the slope, it is now due left, or otherwise towards the back face of the wall. So since we are done with PO, taking now the individual area and the total area, we can now derive the value of our Z bar. And take note that for our Z bar, so we need to apply the moment area about the base of the wall. So 80 Z bar is equal to the summation of the individual product of AI, ZI. Okay, so rearranging now, the Z bar is equal to the summation of AI, ZI all over now our total area. Again, our total area represented with 80 and with our different moment area. Okay, so for our Z-bar now, starting with the green triangle, so we have the area earlier, 396.726 pounds per foot. Multiply that with the moment area, moment lever arm rather. So for our centroid, so for this triangle, this is 2/3 of 6 plus the remaining distance, which is 14. So plus the area of the second triangle, 1,269.524 pounds per foot. So times for the movement arm, we have now 1/3 of the height, which is 6 feet, then plus the remaining distance towards now the reference point at the base, 14 feet. So plus, for the purple triangle, we have now the area 3,360 pounds per foot. Multiply that with the lever arm, which is 2/3 of the height, which is 14. Then plus, for our last, we have the red triangle, the 12,591.6 pounds per foot. Multiply that with the lever arm, which is 1/3 of the height, 14 feet. So divided by the total, that is 17,617.851 pounds per foot. The value therefore of our Z-bar is 6.674 feet. Okay, so for your practice problem, figure 1.25 shows a retaining wall that is restrained from yielding again under at rest condition. So the uniformly distributed load above the slope is 30 kilopascals. So determine the value of the lateral earth force per unit length of the wall. Also, find the location of the resultant measured from the bottom of the wall. Okay, so that's it for the lateral earth pressure for partially submerged soil and with surcharge load. Take care and God bless.